Okay. Today, at our seminar, Gaétan Guillot will tell us about, rational approximations of linear subspace. I hope he will tell us something interesting about angles. So, Gaétan, you are very welcome.
Thank you for the introduction, and of course for the invitation. So yes, I will talk about rational approximation of linear subspaces. So it falls within the fields of Diophantine approximation, obviously. As an introduction, I will maybe recall what we mean by that. I'm sure you're familiar with this notion, but in the classical case. So if we take psi a real number, we look for rational number P over Q such that psi minus P over Q is small, but with P over Q not too complicated. In the real cases, it's quite simple to say that P over Q is not too complicated, is Q is quite small comparing to the differences between psi and P over Q. So it leads to introduce the notion of the irrationality measure of psi, which is mu of psi, is defined as a supremum over all mu positive, such that there exist infinitely many P over Q with psi minus P over Q less than Q to the minus mu. Okay, so it's the irrationality measure, of psi. I will state a few results about it, classical. Dirichlet's theorem, the pigeonhole principle, states that if psi is irrational, then its measure is greater or equal than 2. It's quite easy to show that. A deeper result by Worth's theorem shows that if psi is irrational and algebraic, then its irrationality measure is in fact 2. So it's much more complicated to demonstrate. And of course, it's not an equivalent statement because, for instance, mu of E, the Euler constant, is equal to 2, but E is, of course, not algebraic. So this problem has been quite studied, but it's still an open problem to determine for all real numbers their irrationality measure. For instance, mu of pi is still unknown, but we conjecture that is equal to 2. And for now, we can only bound it by 7.103, etc. It had been quite recently by Zedilin and Zeiberger. Okay. So before ending this introduction, I will mention a special type of number, the Liouville's number. Psi is a Liouville number if its rationality measure is equal to plus infinity. So historically, it has been the first kind of number that has been explicit to prove the existence of transcendental numbers. So for instance, we can exhibit the number y, which is the infinite sum over n of the inverse of 10 to the factorial n, which is a Liouville's number, and we can show that its best approximation, rational approximation, are the truncated sum. So best approximation of y. In my thesis, I'm using those kind of construction to construct subspaces. So I think it's good to mention it earlier. Okay, so this is a classical case, but I'm looking for a generalization of this problem. Generalization. So it's a problem that has been raised by Schmidta in 1967. So the problem is the following. To quantify the approach of a linear subspaces, let's say A, of dimension D in Rn by rational subspaces of dimension E, which are not too complicated. Okay, I state the problem, but I have two notions that I have to define. What does it mean to be closed when we talk about linear subspaces? What is a rational subspaces, and what does it mean in that case, not too complicated? So in the following minutes, I will define those notions. The first one, maybe the easiest one, is the rational subspace. So we say that B is rational if it has a basis of vector with rational coordinates. Quite natural definition. Okay. So if we have a basis with rational coordinates, we can say that B is rational. And to subspace B, which is rational, we will link a notion of complexity. So we define, sorry, maybe first I will say that we define R and E, the set of all the rational subspace of Rn of dimension E. Okay. So to such a subspace, we link a notion of complexity, which is the height. So we define big H of B, the height of B, as the covolume of the lattice B intersected with Zn. So we can under B with the Euclidean structure, and we consider the lattice B intersected with Zn. We take its covolume, which is the volume of its fundamental domain. Okay. So how do we calculate those kind of heights? The easiest way is to exhibit a Z basis of the subspace B. So if x1, xe is a Z basis of B intersected with Zn, then the height of B is equal to the norm of the exterior product xy to xe. Here, all my norm will be Euclidean norm, so it's well defined. Okay, so for instance, and a few examples, we can calculate the height of the line spanned by the vector 1 pq. This is square root of pq squared plus q squared, because the vector pq is the Z basis of the lattice of B. Okay, so I've defined two notions. I have defined what does it mean to be rational and what does it mean to be not too complicated. We say subspace B will not be complicated if its height is quite small. And it remains to define the proximity between two spaces. But before that, I will maybe talk about proximity between two vectors. So let x and y two vectors of r to the n, and we define the angle between x and y as the number of psi of x and y, which is the norm of the exterior product between x and y over the product of their norm. So we call that angles, but it's really the sign of the angle made by those two vectors in Rn. So absolutely, I need to be sure it's the right sign. Okay, so it's a quantity which is in 0, 1, and we will say that x and y are close if their angles is small. Okay, so now I have to I can define what does it mean that two subspaces A and B are close. So from now on, for this talk, I will just place myself in the case D plus E would be less than 1 than n, in order to simplify the definition. So let A be a subspaces of Rn of dimension D, A be a subspaces of Rn of dimension E. So we will construct T is equal to the minimum of D and E angles between A and B. So the first one will be psi1 of AB as the minimum of the angle made by vector of A and vector of B. So it's the first angle, and we define also x1 in A and B, y1 in B, such that the first angle is in fact the angle made by those two vectors, x1 and y1. So we will make an induction to create to define all the other angle. So we define A1 as the orthogonal subspace of x1 in A, and B1 will be the same for B with y1 in B.
Sorry, but
Yeah.
as I see, minus x sub 1 and minus y sub y sub 1 is minimal 2. How we is not uniquely defined, or we need not such fact.
They're not unique, but they exist, and it's
so that is not unique, but this is some x1, x sub 1.
yeah. Yes, of course.
But x1 and minus x1 always have the same angle with. So
yes, it's more the line. We consider the line more of the vector.
Generally speaking, we consider projective coordinates.
Yes. So I choose one x1 and one y1 to construct A1 and B1, and I can go on and set that psi2 of AB will be the minimum of the angle made by vector x and y, but for x in A1 and for y in B1. So if it's the first angle, but for the subspace A sub 1, B sub 1. Of course, we have the relations that psi1 is less than psi2, and we can go on by induction we construct psi1 less than psi2 less than psi-t, which is the minimum of the dimension. We stop when we are no more dimension left to construct the orthogonal, so we have to stop at psi-t. Okay, so from now on, we can say that A and B are close for the J angle if psi-j of AB is small. So I have defined all the three notions I have to state properly the problem. But maybe before generalizing the rationality measure in the case of subspaces, I will make a quick remark that if A and B intersect, sorry, this is the dimension of A intersect with B is greater than J, then so it's not really interesting. So we have to define a notion of irrationality for subspace. So it leads to the following definition. We say that A is EJ irrational if for all subspaces which are rational of dimension E, so in R and E, the dimension of A intersected with B is strictly less than J. So the J angle is not 0. And we define I, N, D, E, G, J, the set of all subspaces of dimension D, which are EJ irrational. And for such a subspace, I can define an exponent. So it leads to the final definition.
Sorry, could
Yeah.
you be so pleasant and repeat the definition of SM of the last
The last definition, it's
the last definition.
Y N D E J is just the set of all subspaces of dimension D in Rn, which are EJ irrational. So which intersect every rational subspace of dimension E by with respect to this relation.
But you deal under the condition that the sum is less than less or equal than the dimension.
Yes, yes. We have in this talk D plus E
Yes,
with less
less.
so
Sorry, this is all subspaces such that
yes. So that
it's a their dimension is D.
yes, and they respect this condition. The condition
They intersect with this given subspace, yes?
So we fix some subspace or for what?
Yes, please repeat once more.
Okay, so we say that a subspace A is a J irrational if for all B of dimension D, E, sorry, it intersects with less than dimension J.
It is irrational if it is oh, sorry, we did not follow the quantification.
So we say that A is EJ irrational if for all B rational of dimension E, it intersects with dimension strictly less than J. So that the angle, the J angle between A and every subspaces rational will be not 0.
Is there a notion of a completely irrational, something like n-1, 1 irrational?
Yes, of course. It's linked to that. But we can define exponent if we have
you said intersect, but it should not intersect.
It should not, but
It should intersect trivially.
Yeah,
Intersect trivially. So I do not follow the last word, trivially.
Yeah,
It is just the definition as it was in Vasya Nekrasov's paper. Yes, trivially.
Yes.
So it intersect by just zero, or zero.
Yeah.
Oh, yes. Now everything is okay. I all the time was missing the word trivially.
Trivially, yes. Okay.
So, yes, I understand the S sub n or such that there are all subspaces of dimensional D such that they are IG irrational.
Yes.
Thank you.
Doesn't intersect any subspace of dimension G. Dimension, what is the letter?
E.
So Psi sub G is not zero.
G is not zero.
Yes, Psi sub G is not zero. Intersection means zero angle.
Yes.
So if it is not zero, yes. For any rational B. Yes. Okay.
TG PA, sorry, different than zero. Okay. Okay. So with that, I can generalize the definition of irrationality measure for such a subspace. So I take a subspace of dimension D, which is EJ irrational, and we define the exponent mu n a e j as the supremum of over all mu positive, that there exist infinitely many rational subspace of dimension E, for which the angle made by A and B, the J angle made by A and B, would be less than the height of B to the minus mu. So it's very similar than the rationality measure for real number. In fact, I will mark the rationality measure of psi of real number is equal, in the case n equal to approximate the line spanned by one psi, when we try to approximate it by line on the first angle. Okay. Is that definition clear?
Yes.
Okay.
Everything is fine. Yes.
So the goal of my PhD thesis is to know how to calculate some exponent for given A, E, and J. And in this direction, I could state a few results made by, for instance, Elio Joseph in his PhD thesis in 2021. He proved that there exists A of dimension 2 in R4, such that the exponent in R4, so nu4 A2 when we approximate by plane in R4, but for the first angle, is equal to 3. Why it's important? Because it's optimal in the sense of the following statement, that for all subspaces of R4 that live in R4 2 to 1, or 2 1 irrational, we have mu4 A21, which is greater than 3. It's a result of Schmidta in this paper. Okay. So we can find a subspace A which relies the exponent 3 in R4. Okay. So it's one kind of problem we can solve to look for the direction. We can also study the spectrum. So the goal is to describe all the value taken by such exponent un a e g for a spanning all the d e j subspaces. So I will call that S and D J. And in this direction, we have a result of Laurent, which calculates the spectrum in the case D is equal to 1. So obviously the first, we have just one angle, the first one. And the value taken by these exponents are the interval n over n minus e to the infinity. In the same, sorry, yes.
One moment. This is a result by Laurent.
Yeah.
Considered. What did he consider? He considered. What is one here?
So he tried to approach a line in Rn by subspaces of every dimension possible. So,
One dimensional line by
yes,
subspaces, and you are looking for the angle.
the first angle. So with the line, we just have one angle.
First angle means the closest.
Yes, the
space.
closest. Yes.
And this spectrum of exponents contains if we deal with approximating by one-dimensional subspace, what do we have?
The value taken by this exponent will be the interval n over n minus 1 to the infinity.
N over n minus 1. So it is, the optimal should be 1 over n so it is weaker in dimension for ordinary simultaneous approximations. It is weaker than we understand, but it is important that it works for higher dimensional subspaces. Yes, is it? Am I right?
I'm not sure I'm following.
When we approximate by one.
Yes, so S
dimensional subspace.
and 1, 1, 1.
Yes.
We find
from Laurent, it is from this value. It is not so good as because if we have approximation to one line, it is by integer vector to a line, it is simultaneous approximation. And
yes.
simultaneous approximation, the exponent will be can be any exponent from Dirichlet exponent 1 over a, or it is just Dirichlet because it is 1 plus 1 over m minus 1. It is just
There's a one missing
result.
somewhere. It's not exactly the same exponent we used to consider.
Dirichlet gives in this case just m over m minus 1 because it is 1 plus 1 over m minus 1. We have m minus 1 numbers.
Yes, my exponents are not really the same that usually consider in.
I see.
Yes.
But sorry for a stupid question, but I don't understand why this spectrum does depend on I. So if we have some line, rational line in M in M dimensional, and if we have some rational subspace, and we have some line in this subspace, and we have the angle between these two lines, we can consider this line.
No, because it can be irrational.
Yes, in some rational subspace with that we have irrational lines which can make a better exponential, a better angle actually. Okay.
Is it true that the endpoint corresponds to Dirichlet bound, which comes from finding n in so what is it? The E independent approximations close to a line.
I think so.
Yes, it is. I see. So it is the left bound is something from Dirichlet, and everything, any exponent greater than this exponent may occur.
Yes, but the generic exponent, I think in that case is the lowest one.
The generic exponent is the lower.
Yes.
Yes. It is clear because almost all lines are badly approximable up to say logarithm.
Yes.
And for badly approximable, we can catch a lot of independent points close to it, and then generically, if you say about measure one, then the exponent is the left-hand side. Yes. Oh, it's clear. It's clear. Wonderful. I am sorry because usually we use different exponents.
Yes. I should mention it before, but yes.
you need to recalculate it in mind.
Sorry. I should mention that.
What it is about. Okay, fine.
So this is for the first angle, actually, for a line and for the first angle. A different angle, which is quite silly, is the last one. Why the last one? Because in that case, psi d look like a distance on the Grassmannian variety. So maybe we have some result like this one by De Saxe in 2022, so quite recently. So it says that for any dimension, but when we study the last angle, and the last angle is realized by the minimum of the dimension, we have a similar result. All the value taken by this exponent are an n over minus dE, minimum of dE, and n minus maximum of the dimension. So we generalize the first result in the case of the last angle, which last angle is.
So sorry, what in the denominator?
The minimum of dE factor n minus the maximum of dE. Okay.
Factor or what? I did not see good enough. Sorry.
I think that in the denominator there is product minimum times m minus
Yes.
maximum.
Yes, it's a product. Sorry, my handwriting is quite bad on the tablet. Sorry. Okay. So this is the spectrum for just one exponent. We fixed 4 value n, d, e, g, and we study the exponent. But we can study another type of spectrum, it's called joint spectrum, which is the spectrum of a family of exponents. So we fixed d and n, and we pose and we define vd n as all the ej corresponding you can study. So e will be in 1 n minus d in our case, and g is the angle, so it will be in 1 minimum of dE. So we study the image of function, so of ej for ej in VDN, and we try to consider the image to compute the image of such function. We just fixed dn1.
We look together for different exponents. So we fix a, and we want to approximate this a by b's of dimension e with different e's.
Yes, yes,
And for ease, we also consider J. J means the number of the angle.
yes. Can study. Yeah.
And we are we are interested some subspace with approximation in approximating by subspaces of a given dimension, and we are interested in a given angle, but dimension and angle, this pair can run through a set. If set consists of one element, it is just what was studied
Yes.
before, and we can consider, for instance, set which consists of two elements.
Yes. Or more.
Okay.
For instance, if d is equal to 1, and we study the image of the tuple mu n 1 1 to mu n 1. Sorry.
But look, one question.
Yes.
If you consider different pairs EJ,
Yes.
EJ and EJ prime, then the values of the corresponding exponent may be dependent.
The image of, sorry, what?
You consider two exponents which
Yes.
correspond to one pair EJ and to another pair EJ, maybe with the same E or with the same J.
Yes.
Sometimes I think that the measures will be dependent. It means that if you know a value of one measure, then it gives a restriction to the value of another one.
It's a kind of question we ask ourselves. So
It
we
is
can,
just what are you interested in?
yes, we can wonder
Excellent.
if there are some algebraic independency in the exponent, but I think they are not. So I will come to that later. So in the case of dimension 1, we try to compute this tuple, the n-1 tuple. Is the image is known, and it's different result by Schmidt, Laurent, and Damner-Roy, which determine all the n-1 tuple that are in the image. And as a corollary of those kind of result, we can say that as a function, those exponents are algebraically independent.
Is this a joint paper, or you put together different papers and
Yes.
different results?
Different result, yeah. So it's not
It
clear,
looks
but
like, it doesn't look like Schmidt. It looks rather like Roy.
yes, Roy did the main work, but Laurent this image is defined by some inequalities. Laurent states the inequalities and or proves that they are optimal.
Laurent states general inequalities in this setting.
Yes, but Schmidt and Laurent used the going up
Schmidt
and
and
going down
Laurent,
theorem.
Schmidt and Laurent formulated the inequalities, wrote down the inequalities, and Roy proved the optimality.
Yes, by using parametric geometry of number.
This is because of d equal 1. You can use parametric geometry. We do not know how to use parametric geometry or numbers in the case what was solved by Elio, for instance.
Yes, it would be wonderful if we have such a theory, but I don't know how to.
Okay, fine.
So, but in this joint spectrum, we can find an open subset with a non-empty interior. So it leads to the corollary. Those functions are algebraically independent over R. So such a question of dependency are solved in that case.
Sorry, do you mean they algebraically independent, in which case, like a function from space of matrices to the R, or what?
Like function on the Grassmannian subspaces.
There is no relations between them. Even
Yes.
I think even more than algebraically independent, there is no even non-algebraic relation, as far as I understand.
Yes, because they are
If
an
there
open
is an
subset
open
of the,
set, then
yeah,
for
yes, yes.
instance, analytic relation will give a
Yes, yes.
manifold of codimension 1 at least, and then there
Yes,
will be no
yes.
open set.
Yes, yes, of course. So it's we ask the question because, for instance, in the case of uniform exponent, we have some relations type Jarnik type relations between the exponent in the case n is equal to 3 or 2. It
But
depends on the settings.
You did not speak about uniform exponent
Yes,
for angles.
but yes, I will not speak here about uniform, but I will just say that in their case there exists some dependency.
In general, there exists some.
Not in general, but there's some case with dependency, so it's not obvious that all the exponents are independent. Okay.
Yeah, I don't understand. For me, it is not obvious at all that they're
Yes.
independent.
Yes, yes.
So you shouldn't explain it. But if you say that you look for uniform exponent, I'm wondering because I do not know any result on uniform exponent for angles besides those which can be easily deduced from Schmidt.
Yes, but for uniform, I guess a bit more. No, I'm not an expert on uniform exponent, so I won't say. Sorry.
Okay. You do not consider the topic of uniform concerning uniform approximation. Okay.
Yes. So what I proven in my thesis that for the a fixed dimension, which could not be one, that we consider the family of all the exponents. So in the n that I explained earlier, is a family of transcendental degree over R at least n minus d. So I can explicit a subfamily of this exponent of cardinality n minus d, which have no relation. Okay. Is there any question from here? I will start a new section.
Do you mean that is it important for you that you are looking for algebraic relation?
I always take my result as algebraic, but yes, in analytic and other functions.
I think it is not it is not necessary to in fact I guess that you assume a stronger result, that there is no not just algebraic relation.
Yes,
but say something like very smooth relation.
Yes.
Okay.
I should say that
Because
yes.
For non-specialists, this may be a little bit curious because they're thinking algebraic relation, but in fact you do not deal with algebraic relations. You see that there is no dependence.
Yes. I should say that instead. I find an open subset in the image, so yes. I can say whatever I want. Okay.
In fact, your main statement is that there is an open set in the image.
Yes, I should say that. But
okay, and this is a corollary.
Yes. Okay. So how do I find open subset in the image? My main tool is the construction of subspaces with prescribed exponents. What I call exponent is the measure I don't know how to call them because there's so many parameters, but yes, I call them exponent, Diophantine exponent. So I construct subspaces with post-coequivalent, which means that I can construct subspaces which I know how to calculate their exponent associated. So I will maybe state first the result in the simplest case. D is equal to 1, so J is equal to 1 also. So what can I do? In my theorem, I take alpha, a real number greater than 2 plus n minus square root of 5 minus 1 over 2. And I state that there exists a line, so of dimension a line A in R to the n, such that A is n minus 1 irrational. So it's not contained in any rational subspaces of Rn, and for all E in 1 n minus 1, I can compute the exponent, which is equal to alpha 2 to E.
Oh, well, few questions, two questions.
Yes.
Do you construct A? You look for a vector which determines A. Do you construct it as a series?
I construct, yes. I will explain the sketch of the proof.
Then second question. Haven't you looked in recent papers by Johannes Schleichitz?
I'm not sure. No.
Okay.
So-
Sorry, it is every alpha in this, or it's Louisville.
every alpha.
Alpha is
Indeed.
not Liouville because it is not in the point infinity, but somewhere.
Liouville number will appear somewhere, or kind of. Liouville.
I also have one question, not for the speaker, but for the audience. А где Ренат Ахунжанов? Where is Ахунжанов? Это вообще безобразие полное. Так сказать. Тут про него говорят, он сам не знает, и никто этого не знает, и его нет. So, I am angry that one of our specialists is not among the audience. So you may continue. So very.
So I will try to explain the proof here. So how do we construct such a line? So construction. So A will be the a line spanned by a vector y, and y will be of the form 1 sigma n minus 1, so a vector in R to the n, and sigma y will be constructed as a Lewis number, but will not be one, as the infinite sum of uky over theta to the power alpha to the floor of the power alpha to the k. So with, let's say theta is equal to 5, we can take every prime number great enough, but 5 is okay. And uky is the sequences we take its value in 0 to 1. 0, 1, 2. So why do I let uky have so many 3 value? We can choose.
Sorry, theta raised to the power, which power?
The power
D.
is the floor of alpha to the k.
Alpha to the power h. Alpha is this ratio which respond on exponent, and to the power h means that the next denominator is the previous denominator to power alpha. This is necessary to construct the corresponding value of mu.
Yes.
And so, sorry, so we have, and theta is, you have wrote that theta equals to
5. Let's say 5.
5.
But we can take every prime number great enough.
Oh, thank you.
Theta may be taken to be 5. You see, it is not a Liouville number. The growth of the convergence of the series is not so quick, but nevertheless.
Yes. In fact, we can prove that the irrationality measure is in fact alpha here. But it's not a Liouville number, but it looks like the construction is inspired by Liouville's number, let's say. Okay, so I will choose value of u, okay, y, such that 1 sigma n minus 1 are linearly independent over Q. So it gives us the fact that A, so it's a vector span by Y, which is a vector of 1 sigma n minus 1, is n minus 1 irrational. So we can choose such a sequences, and we do. So we can now calculate the exponent associated to A.
But how can we choose such? Is it obvious that we can?
We have such a dependency on the sigma are countable. They are just countable. Sigma y that realize the dependencies of if I have...
so it's from the cardinality.
Yes.
Because it's not countable. It's continually many ways of choose such a set of u sub h and y, but it is not big enough set of linear. Thank you.
So I choose such sequences to have this irrationality property on A. So now I can compute the exponent. So what do we do to compute the exponent? We look for the best approximation of A. And as in the construction of Liouville numbers,
so you are able to calculate best approximations for you mean simultaneous approximations?
Yes, I don't know if we have the same vocabulary for everything, but I find that I will find subspaces that realize the exponent alpha to the
yes. You should look into once you should look into Schleierschild's papers.
Yes,
he's doing
surely.
something like this to calculate, but he was interested in uniform.
Yes.
Uniform exponent, but he was able to simplify a lot of things just by considering similar series.
Okay.
Excuse me, which power of alpha in our formula?
E, alpha to the E.
H.
H.
H, of course, yeah.
Yes.
Okay, thank you.
Because at each summand, at the next summand should be a power of a previous summand to alpha, an alpha power.
Yes, yeah.
Purpose we have alpha theta to the power alpha and alpha to the power h. So the next one is the same to the power alpha.
Yes. So I will try to show what are the best approximation of y. So I will start by truncating the sum as a Liouville number to approximate best my sigma. So my sigma y. So I truncate the sum to big N, So just look at y over theta alpha h. And this is a rational number, and specifically it's in 1 over theta to the power alpha n times an integer. So we define Zn as the vector 1, sigma 1, and sigma 1 and minus 1. So it's a rational vector. And we have
Sorry, sigma 1 n, and
yes,
what? And the last vector, the last number is sigma 1
n minus 1. I do that for all my my sigma.
Sorry, n and
Sorry,
you have capital.
what? Okay, sigma n minus 1, small n minus 1.
No, that's
Just one comment or one question. In your construction, for different sigmas in each summand, the denominators are the same.
Yes,
It's true. So you have the same denominators, but you are varying numerators from a finite in a finite set.
yes,
Yes. So you have the same denominators.
yes. It's important actually.
Yes. Okay. I see.
So I truncated my vector y to Zn actually. So I truncate every sigma y to sigma I. So there I have a vector Zn with a truncate y's. So the norm of the different y minus Zn is approximately 1 over alpha to the power n plus 1. It's by construction. So I have a vector which will approximate well y, but I need subspaces. So we fixed from now on E, the dimension of my rational subspaces that will.
sorry. One, which power? We have the distance is like the sum of our series approximately.
Yes.
But as I think it's no, it is at n plus 1, but we can estimate the sum of series by integral due to Cauchy's theorem, and from this we have not that degree, or I am a mistake.
I'm not sure I understand the question. For considering the
I think that it is not dn plus 1. I think
it's alpha.
Oh, so sorry, alpha.
Alpha.
I think it is not alpha raised to the n plus 1.
What do you think it is?
Give me 1 minute. I think minus 1. I think something like minus 1.
We have sigma y minus sigma n minus 1. We start the sum.
The sum from n plus 1 to the infinity.
Yes.
Yes, I think it's theta raised to the power alpha n plus 1, but minus 1. Alpha raised to the n plus 1 minus 1. I think so.
Where does the minus 1 come from?
It is come from the like we can estimate such a function. Sorry, we estimate by ash, not by theta. Sorry.
The sum is on h. Yes. Is that okay? Okay. So I have constructed a vector which approximates well y, but I need to construct a space. So we define So we define B and E as a vector subspace spanned by Zn plus 1, Zn plus 1, Zn plus E minus 1. So we can choose the sequences UHY with UHI, so such that the dimension of being E is in fact E, so not too difficult, and we know the height of E, and is approximately theta to the alpha to the n. So it's we have a choice to make here for the sequences, but we can do that to have those property on Bn. So I have constructed rational subspaces B and E, which I know the dimension E, of course, what we look for, and I know the height of B and E, and now I will try to see how it close to A. So I will bound from above my exponent, and I will state a few lemma on the proximity between A and B and E. So what I state that the first angle between A and B and E is approximately theta, sorry, 1 over theta to the power alpha n plus E. How do I prove that? So it's my notation approximately is in fact a big O of theta to the alpha to the n plus 1. So to bound from above this angle, I know that Zn plus E minus 1 is in B and E. So the angle between the first angle between A and B and E is less than the angle made by Y and the Zn plus E minus 1. I can calculate this angle. So it's a norm of the exterior product of the two vectors over the product of the norm. I can subtract Zn plus E in the first vector. It doesn't change the exterior product. And I still have the same vector on the denominator. And I can bound the norm of the exterior product by the product of the norm. So it only remains Y minus Zn plus E minus 1 over the norm of Y. And as I stated before, the difference between Y and Zn is approximately 1 over theta to the alpha n plus E, because we have n plus E minus 1 plus 1. And to bound from below is technical.
Sorry, could you repeat how we last estimate? Could you understand how we obtained
it came from the definition of Zn. We have this estimate on the norm. Y minus Zn is approximately of norm 1 over.
No. Before.
This one?
No, yes, this one.
We can bound the norm of the exterior product by the product of the norm.
Thank you.
Okay.
It's obvious. Sorry.
Sorry. Okay. So I estimate the angle between A and B and E is equal to the inverse of theta to the power alpha n plus E. So I know the angle, I know the height of B and E. So I I have that the angle, sorry, finish. The angle between A and B and E is approximately, so theta minus n plus E, which is approximately the height of B and E to the power alpha to the E. So we can conclude that the exponent mu n r e 1 is greater than alpha to the E. So bound from below is quite the easiest part of every approximation we make in my thesis. The complication are the two bound from above. From above, mu n is 1. I will not go into details, but what do we make? We show that in fact the subspaces B and E are the best approximation of A. So we have a lemma that states that let epsilon be positive and B and C a rational subspace. Sorry, rational subspace with such that psi1 of AC is less than h of C to the power minus alpha to the E minus epsilon. So we suppose that C realize a better approximation of A. The angle between A and C is better than the B and E we have before, but the conclusion is that then if h of C big enough, C will be equal to B and E with a certain integer n. So that lead to show that we can do better than alpha to the E. So a fortiori, UNRE1 is less than alpha to the power E. Okay, and maybe I just state that in this lemma appears the condition that alpha should be greater than 2 plus square root of 5 minus 1 over 2. And if you have a question, I can specify a bit, but
yes, it is not clear where this condition comes from.
I'm not sure I will be able to go deep on the detail, but maybe I sketch it.
But look, one question. Do you construct? Can you say that? So you have you consider the one partial sum of the series, and it generates a certain rational subspace.
Yes.
Then you consider the next partial sum of this series.
Yes.
And it generates another subspace, and you know the upper and lower bound for the angle between each of these subspace and the resulting line. Yes, isn't it?
Do I know the angle between Zn and Zn plus 1 actually? That's the question.
You know the
No, I'm not sure I understand the question.
you give if you want to have lower bound, if you want to have upper bound for mu,
yeah,
it means that this is a lower bound for approximation, isn't it?
yes.
And you claim in lemma upper bound.
I claim that we can have better. We can have better than alpha to the E. If we are better, in fact, we are a Bn plus in B and E space. So we can do better than B and E. B and E realize alpha to the E. So we can have better. So it leads to the conclusion.
If it is better, then
It's
some dependence happens.
yes, it's contradictory.
If it is better, some dependence happens, so it is not better.
Yes, it's
I have many questions, but probably so another one. But first of all, please do not worry. So I think you have as much time as you wish. So it is better, but it is better to ask questions and listen to answers. So one moment, when you construct this, these approximations, can you say that these approximations are best approximations in terms of the angle? Or you do not know if there are better approximations in between?
in terms of angle, I don't know, but when we're linking to the height of the space, that's the best. But I'm not sure.
In terms, probably there are best approximations in ordinary term, in ordinary sense, in sense of simultaneous approximations.
Probably, but
You did not check it. You did
I
not.
I did not check, and my goal is to construct spaces with higher dimension. It's the first case is d equal to 1. It's a simultaneous approximation, but it's not my main goal. So it's just a step in my construction, I guess. Okay.
Okay. Well, let us continue.
Okay. So how do I prove that C is in fact B and E? What I do is we show that Zn is in C and Zn plus 2, Zn plus E minus 1 is in C. For that, we compute the angle between Zn and C. And we have only triangular inequality on angle. We can say that it's less than the angle made by Zn and Y plus the angle made by Y and C. But we know this angle, the first angle is approximately theta to the power alpha n plus 1. And the angle made by Y and C, as an hypothesis of my lemma, is h of C to the power alpha E minus epsilon. So with this,
sorry, but why we have such inequality?
I didn't state it, but it's a triangular inequality that quite natural to look for.
We have for that function we have an triangle inequality.
Yes.
This is something
As
in school geometry, triangle inequality for angles.
Yes.
For
not for subspace, but for angles. Yes.
For angles.
Yes.
Certainly, yes.
Okay. So by this inequality, we find n such that say Zn C is small compared to h of C. So I'm a bit faster on the detail, but it's very just calculating approximation, and so the angle between Zn and C is equal to 0 for a certain n. So it leads that Zn is in C, and we do that for all the Zn to Zn plus minus 1.
We try to find n such that
is small, so that the angle made by Zn and C is very small compared to h of C.
And what we know from this fact, what we know that this angle is small enough, and what we have from this.
If it's small enough, we can prove that the angle is in fact zero.
So because this rational space,
Yes, yes.
subspaces.
If the angle between rational vector and a rational subspace is very small, then it's zero. So we can prove that Zn is in fact in C, and we do that for all those vectors, which leads to Bne in C. So it's we have the equality, and we can conclude. Okay, so it leads that if we have a better subspace C that make a better mu, it's not really possible because in fact it is Bne. So it's bound from above my exponent. So I bound from below and bound from above my exponent. I have proven my theorem. Okay, so maybe I will just finish by that. But if you remember, I motivated my theorem by looking for exponent with no relation between them. But what I have constructed is exponent is equal to alpha to the power e. So there are obvious relations between those exponents. But what we can do, we can transform the sequences alpha h, which appear in the construction of the sigma y, to sequences alpha sub h, and then UNAE1 will be equal to the limit superior of alpha h plus e over alpha h when h tends to infinity. So it's the same tool we use to construct this space, but we can allow more value to be the value of the exponent. And in this value, we can with that we can prove that an open subspace in the image of all the exponent of the family of all the exponent. So that's what we're doing. Okay, I will finish soon, but maybe I will state what we can do, what I can do best. My main theorem is that if we suppose that D divides N, then we can construct a subspace A of dimension D such that we know all the exponent UNAEJ if E is in 1 n minus D, J is 1 minimum of the E, and D times E is strictly less than J times N. So I can construct a subspace of dimension D for which I know a lot of exponents, just they have to verify this this condition, this hypothesis. How do I do that? A will be of the form A1 plus A2 plus AD with AY a line that come from the first theorem. And by making those calculus, I have a property which gives me the exponent for a sum of a line. So I can compute all the exponent I state in my theorem. Maybe I will stop here, and time remain, we can follow up by question. But I think I will finish my talk here. Thank you for listening.
Thank you very much. Oh, one moment, I don't understand. Thank you. Any questions, comments? Thank you very much. Thank you very much. It was very interesting. So to summarize, you construct explicitly
Yes.
the spaces, the irrational subspace and it approximating spaces in terms of series. You construct, you may say, the basis of these spaces step by step inductively.
Yes, yes. And,
Okay, so any questions, comments? I think it would be, it may be useful for you to look for a very, not very, few recent papers by Schleichens, where
Yes.
he, by means of not similar series, he considers series with different denominators, but the denominators are included. They divide each other. Because
okay.
this means that they are, in some sense, they are common denominators, but you should multiply them to come to the common one. So he is doing this to give examples for Dirichlet spectrum, that is for uniform approximations.
Yes.
Okay, so
Okay.
thank
I
you very
will-
much. Very interesting. So there were a lot of questions during the talk. Is there further questions? Okay, if not, let us thank the speaker again. And by the way, Gaétan, Antoine Marna suggested you to speak, to give a talk once at our general seminar, which we have on Tuesdays as usual. By the way, are
Okay.
you preparing a paper?
Yes, I will write my result in a paper. But I put my PhD on archive.
You
for
put
now,
just
but-
PhD. You put
But
just,
I will put an article, but maybe later.
you're preparing.
Yeah, I'm preparing. So,
Wonderful.
yes.
Because it would be nice to see it also as a paper.
Yes, of course. It's in preparation.
Excellent,
Yes.
excellent, wonderful.
Yeah.
So, any questions or comments? So I hope that then I think you should finish. So Gaétan, I hope to meet you personally, at least in June.
Yes, maybe. Probably. I hope so.
Wonderful.
I have a question.
Yes.
Yes. Is it true that angle between every two rational subspaces can be not zero and very small?
We can bound from below between. Yeah, sorry. If we have, your question is if we have. Sorry.
If we have two,
B and C. Sorry, I can
yes, rational
You're asking about the
subspaces.
construction, about the subspaces from the construction.
No, it's common question.
It's common question.
Yes, about if we have two rational subspaces B and C.
You can bound
And
the angle
they
by
intersect
the
trivially.
inverse of the product of the heights, actually.
Always because if they do not intersect, there should be analogy with rational numbers. If two rational numbers are different,
Yes.
then their difference is greater than
Yes.
1 over the product of denominators.
Yes.
Yes.
Maybe it is simple but very important observation for at somewhere for subspaces.
Yes. We can
you can bound it from below by the product of heights in denominator.
Yes. I can't write anymore. I don't know why. Sorry, my pencil just broke. So
Oh.
I can write
But
it.
well, I can help you. I hope I can help you. So HB, yes,
Yes, and HC.
times HC.
See.
Oh, I'm sorry, it is not perfect, but well, okay, fine. Maybe this is very important. Indeed, it is very easy observation, but it may
Yes.
help.
Yes, it's very similar to the real case.
Yes, because it's
dimension
very
one.
similar to rationals.
Yes.
Because H from B times H from C times product of all angles is integer number, yes?
Yes. Yes. It's in fact the exterior product. We concatenate two bases of
Yes.
the basis of B and the basis of C, and we do the exterior product. We have the product of all the angles.
Yes. If D plus E so what is E plus less than D,
Yes.
less
In
than
this
N, less than N, if D plus E less than N, and they do not intersect, they're independent, their sum is less than the whole space, and we can, and we can concatenate bases.
Yes. But we, in general, we have to be careful on what we consider. We have a different notion of irrationality if we D plus E is greater than N, and so it's a bit complicated to enunciate theorem.
Okay, well, any more questions? So thank you very much.
Thank you a lot to
Probably we will have a break. Our next seminar will be next Saturday, and there will be a talk by Nikita Shulga, who will speak about numbers with missing digits, about some results of from Шпарлинский team. То есть в следующий раз у нас Никита Шульга расскажет об учениках Шпарлинского. Мы вообще, честно говоря, хотим их объесть. Вот. Но вот пока Никита, так сказать, нам расскажет что-то. Okay, so thank you very much.
Thank you.
And now we will have a break. So thank you for everybody for coming. I think с Германом и с Артемом мы собирались поговорить. After seminar, we would like to have some talk after seminar with Олег and Артем. Yes, да? Тогда, да, сейчас немножко передать.
Thank you and goodbye.
Thank you, goodbye.
Goodbye.
Bye.
Я единственное хотел спросить, Николай Германович,
Да.
можно через полчаса собраться?
Давайте, хорошо. Тогда я с Германом еще парой слов. Давайте через... Хорошо, да.
Ага, хорошо.
Ну, не под запись.
Ой! Да, выключаемся.